So uniform distribution is the most basic distribution that we can think of. However, it plays a significant role in statistics. The reason being, uniform 0, 1 would mean every single value that you sample from a uniform 0, 1 would be equally likely. Give me a number that could have come from a uniform 0, 1. 0.0268. 0.0268. Okay, Nathan. 0.0269. Wow.
0.345.
Okay.
0.5.
0.000.
Going in order.
I don't know. 0.2.
0.2.
0.25.
0.26.
I wasn't looking.
0.12.
I was the same words.
It's supposed to be equally likely. This is not a random sample.
It seems. I mean, one.
What did you say?
You got to sit there.
Right. You get streaks.
No, it doesn't matter.
I shouldn't hear you.
It's just a
I
reason
said
why.
0.45.
Correct. Observation between 0 and 1.
I said 0.45.
4, 5, 1, 3. Peter's right.
0.31415.
Great.
We'll put zeros followed by a 1.
I just need a
And
number.
if many zeros, they're all equally likely. So again,
Yeah,
nearly infinite string of zeros followed by 1, and it's just as likely as 0.5.
Oh, I see. Infinitely zeros, infinite zeros.
It's not literally infinite, but you know, rule marks.
Okay, I see what you're
10 to the
saying.
power of
True.
100.
I agree. So all these numbers that you gave satisfy the property of one important quantity in statistics. What is that quantity?
Well, they're from 0 to 1, so they're not possible.
They're all probabilities. So pretty much uniform distribution is the distribution defined for probabilities. So even though it is a very simple distribution, we could do a lot of things with uniform distribution. One of the things is called a probability integral transformation. We can also call this as inverse transformation. Inverse simulation transform. The latter names or phrases came later in time, but back in the day it was called probability integral transformation. So called the fundamental rule of simulation because several sampling techniques, Gibbs sampling, Monte Carlo simulation, acceptance rejection sampling, all of those use random uniform. So heavily used in simulations, which is why we call it fundamental rule of simulation, because if we want to simulate something in probability or in statistics, we need probabilities of something. So what does it mean? Suppose U is a uniform random variable defined on the interval 0, 1. So clearly those are probabilities. And f of x is some CDF. It doesn't matter what it is, but it's some random CDF. And if I said x equals f inverse of u, in other words, I'm plugging in a random variable. In the sense, I'm going to get random values. I'm going to do this using a graph. Then we can move on to a formal way of showing as to why this is true. Suppose I have a CDF, some random CDF. Could that be a CDF?
No.
Right, it can't be. So those are all probabilities, correct? And since they are probabilities, all the values over here will be distributed uniform. Do we agree? Yes. The values here are uniformly distributed between 0 and 1. So this y-axis is simply the random variable u. In the sense I could pick values from u and I'll get these probabilities. Now over here, those are the x values. Mind you, x is a random variable also. What is the support of x? 0 to infinity, even though I get the 24 here, but I can keep on going. So most of the values will end up being here. Give me a nice random number between 0 and 1. Something that is distributed uniform 0, 1. 0.6. Okay. So that is the first random number for you. I'll call it U1. One more.
0.15.
0.15. Right over here. U2. All for that. No one got it. You
No.
two?
Um,
One, I mean, some of the songs are actually good. One more random note.
You two, like, when they release one of their albums, it automatically went on, like, everyone's Apple device. It's the only reason I know that. So it's not there, so it's not that one.
0.95, okay, so you three. One more.
Four.
Ah.
0.4.
0.4, okay, that's good. I have four numbers. Let's see, let's use basic algebra. This is u, that is the function f of x, just the idea. Based on that, I would like to know f inverse of u1. A single value u1, random variable, but I collected a sample of four probabilities. I would like to know f inverse of u1.
yeah, 4.
Right.
4.
Approximate would be good enough. Good. So I sampled u1. I ended up getting x1. Four. Yes. Then I got a random number which you guys gave me, u2. And what is the inverse of u2? What how about 0.75? Doesn't really seem like one. Just sticks at 0.75. X-ray.
That's after.
16, about 16. U4 is 0.4. About 3. Yes. 8.25. How? So 1, 2, fine. I'll set up the 3.2. Good. So I picked random values from a uniform 0, 1, and I had some CDF. Could be anything. So I have some CDF, f of x, and I use f inverse of those values to get x values. Would you consider that these four values form a sample of size 4? Yes. So this is a sample of size 4 for the random variable x. Do we agree? Now, what would the CDF of x be? Right? It has to follow that, correct? That's where these values came from. So it has to follow that. So if I took random values, put it in some unknown CDF, inverse function, inverse CDF, I end up getting a sample that will follow the CDF F. Good. That's what this means. Why do we call it a sampling transform? Because I can sample a random, I can get a random sample from almost any CDF. It doesn't have to look this way. Most of them look this way, but your CDF can look like that. Right? It's flat over here. It's not decreasing. It's flat.
It's decreasing.
Yeah, I saw the marker go down.
Fine. So did it go strictly up? It could be flat and it goes up. Now that's a funny looking CDF, but if I could have it in a discrete form, an empirical CDF, I can generate a sample from this. And if I can generate a sample from this, then I have a density. If I have a density, then I can do all kinds of things with that. Does that make sense? So that is why we call it as a simulation transform or fundamental rule of simulation. We're using an inverse function, hence the name inverse simulation transform, and also the inverse of a CDF is what we call a quantile function. So that's where the quantile name comes from. Good.
Why is it called quantile?
How?
Why is it called quantile?
I'll explain one second now. So f of x is the CDF. So f inverse of x is a quantile function. An easier way to, well, what would be easier to follow? A bell curve or a uniform distribution? Uniform? Okay. Good. Now, we know the probability of x less than or equal to x, which simply is the CDF of this uniform. We derived it last time, x minus 4 over 2. X minus, x minus 2. X minus a divided by b minus a. So that is our CDF. If I asked you, well, what is the probability x less than or equal to 3? That's easy. That is 1/2, right? That's f of 3. We get 1/2. Yes. So that's not in the middle. Slightly better. Okay. 3, and the probability less than that is simply the area under the curve. And that is 0.5. Correct? If 0.5 probability lies below the number 3, in other words, 50% chance numbers, 50% of the sample that we simulate would lie below the number 3. So which percentile does the number 3 correspond to? 50th percentile. The formal name of a percentile is a quantile. Good. Now, how can I get that 3? Well, 3 gives me a probability of 1/2, a cumulative probability of 1/2 when I plug it in f of 3. So this would imply 3 would be equal to f inverse of 1/2. Correct. So the inverse CDF of 1/2 gave you a quantile 3. Hence the name quantile function. Does that make sense? We don't call it a percentile function because the formal name that we use is a quantile. Good. You can look at the notes and tell me. What? Horizontal line. I used it here. You can look at the notes from last time. We found the CDF of uniform. So if you know that function, what is the CDF of this?
So that would be, well, it's X minus A over B minus A, but we have to put on each side. X over 1 is that, I guess U.
So we would have x minus a divided by b minus a for uniform a. So in this case, a is 0, b is 1, x minus 0 divided by 1 minus 0. It's just x. So that would be u. Good. And that's it. Consider some arbitrary function. Fx of x. Yes. So if that's an arbitrary function, fx of x, and I'm saying that would be the CDF of x, the random variable x. So I could replace x by f inverse of u. That was the statement that I made. If you define x to be f inverse of u, then x will have the CDF f. So in this case, I'm going to argue that fx is the CDF of some random variable x. Then f inverse of u will have that CDF. Okay. So f inverse of u for set. Using subscript to distinguish between u and f. So if you go back and read the statement, if I start with an arbitrary CDF and I set X to be the inverse of that arbitrary CDF evaluated at random variables, random values of a uniform 0, 1 random variable, then X will follow that arbitrary CDF. So here, I'm starting with X less than or equal to X. Oops. Now I'm going to invert on both sides. So probability of U would be less than or equal to Fx inverse of X. Hard math. Good so far. Well, if that is true, this is a uniform random variable, that is some number, because we are taking the CDF, evaluating at some value X, not random value, some fixed value, and we're trying to find the probability U less than or equal to some number, and that number, we'll call it U. What would that probability equal to? You, me, you. That comes from up here. Yes. But what is it? U is Fx of X. So we just showed that the random variable X has the CDF f sub X. Good. So if I start with a random function, a function that satisfies the properties of CDF, and if I use randomly sampled uniform values and put it in the inverse function and define that as a random variable, then that random variable will end up having the CDF that we chose. And that's just what we did here. If I set U to be the CDF right, last time we set X to be the inverse of the random variable U. Now, we know that Fx inverse of X is uniform 0, 1. I'm not saying U is uniform yet. All I'm saying is U, I'm going to set the random variable U to be the CDF of X for different values of X, the random variable. X. So we want to find the CDF of U. Good. And that's what we would have. So I've not concluded U to be uniform 0, 1 yet. I'm heading now. So I'm starting with the CDF U less than or equal to U. And X is less than or equal. Now, since Fx of X is less than or equal to U, the random variable X will be less than or equal to fx inverse of u. Agreed. With me so far. But what is the CDF of x? I'll call this little x. So, or should we use a different letter? We'll just use lowercase x. So, what is the CDF? Because probability x less than or equal to x is simply the CDF fx of x. Correct. So, I can rewrite this as fx of x. Yes. Which would mean I will have fx, replace that value by fx inverse of u. What would happen to fx and fx inverse? They will get cancelled. And I get u. And clearly u has to be between 0 and 1 because this is a CDF. So I end up getting the CDF of u to be u for u between 0 and 1. Good. Yes.
So what was the whole purpose of the thing in orange? Because I thought we showed the probability that x was less than or equal to x was u.
Probability x is less than or equal to x is u. Right. So here I'm setting x to be the inverse of the CDF of x, some arbitrary CDF of u. And I'm telling you, u is uniform. Okay?
Okay.
And then it turned out that whatever arbitrary function that you choose, and you plugged in u, gave you the CDF, which is CDF of the random variable x, which has the CDF fx, the function you chose. Over here, I'm saying, well, x is some random variable that has a CDF x, fx of x. And I'm setting some u to be fx of x. I'm not saying what the distribution of u is. Okay, it is just some random variable. So our point is to find the distribution of u. So I start with probability u less than or equal to u. Go with the fact that u is fx of x, right? So I replace it. I come to the conclusion that x is less than or equal to fx inverse of u. That is a single value, right? I'm evaluating at a single u. So all of that is no longer a random variable. Rather, it's just a single value that's in the support of x. So since this simply is the CDF of x, I can do fx of x, right? Now I'm replacing x by that to get u. That's what I've established. That being said, the CDF of u is u. U is defined between 0 and 1. The question that I'm trying to answer is, or trying to find an answer for is, what is the distribution of u? That is the purpose. It's a lengthy explanation, but that's the purpose. I want to know the distribution of u. What is it?
Uniform.
Uniform, right? Going back to what we did earlier, the only distribution that would satisfy that function is a uniform. So U is uniform 0, 1. So in this case, what we're trying to explain is if I know that a random variable follows a certain CDF, and if I set some random variable u to be equal to that CDF, that random variable will be a uniform 0, 1, correct? Earlier when we did that graph, I said, oh, the y values are between 0 and 1 has to be uniform. I did not justify it. I just said it has to be uniform. Now you know that it is in fact uniform. Does that make sense? Okay, so that's the forward case. Reverse of that is this.